Today, let us discuss the Schrodinger's versus Heisenberg picture. Okay. Let me consider two objects around 5 centimeter apart. Okay, object 1 is A, object 2 is B. I need to displace this object into another 5 more centimeter apart. Okay, so the distance between the two objects should be 10 centimeter. I can move either A or I can move B. However, the distance should be 10 centimeter. It doesn't matter whether I am moving A or B. Here I am going to consider two kinds of approaches. Okay, similar to this, because whether I am moving the object A or B, no matter when my concern is only the distance between or displacement between these two objects. Okay, whether I am moving A or B, whether I am shifting the object A or B. Here I am going to consider the same concept that is the Schrodinger versus the Heisenberg's picture. Okay, Schrodinger's picture is state gets vary with time, and Heisenberg's picture consider observable vary with time. These are two different perspectives on same matter. Okay, before going into depth in detailed study, let me consider a unitary operator. Usually the unitary operator change a ket into another ket. Okay, here alpha is a state ket and the unitary operator operating on alpha, and we will get another ket. Okay, and when we are taking inner product of two state gets, for example beta alpha, inner product of beta alpha, if we are shifting this bra beta into u dagger beta and ket alpha into u alpha, there will not be any change for this inner product of this two state gets, because u dagger u is equal to an identity operator, an identity or u dagger u equal to 1. So this will not make any difference in this inner product. Okay, this transformation affects the state gets. This u dagger affects u dagger, and u with alpha and u dagger with beta affect the state gets, but not operators. Let us consider about an operator x, and we are taking an inner product with the two kets. One is x alpha and another is beta. Okay, so when we are taking the inner product, we can write, we can transform this bra beta into u dagger beta, and we can transform this alpha into u alpha, and this operator is operating on one of the kets. Okay, either this ket or this bra. Okay, that is equal to, we can mathematically write as beta u dagger x u alpha. Okay, by using associative axiom, we can write this beta u dagger x u alpha equal to beta u dagger x u alpha. Okay, these are two approaches by mathematics. That is, here first we need to transform this state alpha into another state, and this bra beta into another bra, and first of all we are doing this operations, and then we are applying an operator. Okay, so here what's happening, the state is changing. Here the state is changing, and that is equal to, we can write like this using associative axiom. This both are right, so we can use this beta u dagger x u alpha. That means here this operator is changing. Okay, that operator x is changing into u dagger x u. Here the states are changing, operator is not changing. Here operator is changing, states are not changing. These are two mathematical approaches. Mathematically we can write this one equal to this one. Okay, physically what it means, that we are going to discuss. The approach one is the state ket alpha is changing into another ket, that is u alpha with operator unchanged, like this. Here this operator hasn't changed, instead the state gets changed. Okay, this ket alpha changed into u alpha, this bra beta changed into u dagger beta. Okay, this is one bra and this is another ket, and the operator remain unchanged. Okay, and here the operator changed into u dagger x u, but the state gets remains the same. These are two approaches. Like whether we are moving A or B doesn't matter, because our concern is the distance or displacement between these two objects. Here nothing is changing, only our perspective is changing. Okay. Let us take an example of translation operator. Example as translation operator t dx dash. Approach 1, the operator is not changing. Okay, that is t of dx dash affects the state gets, not the position operator. This is a state get alpha, and we are applying a infinitesimal translation operator dx dash on it, and that is in the form of infinitesimal translation operator we have discussed in previous classes, that is 1 minus ip dot dx dash over h cross alpha, and the operator remains unchanged. This is approach 1. And the second thing is approach 2. The state get remains the same, that is alpha is not changing with respect to time or something else, or alpha is not changing with respect to time, and the operator x is changing. That is actually the translation operator we know, this is a unitary operator, and operator is changing as in this way, that is 1 plus ip dot dx dash. This is u dagger, this is x, and this is u, and that is equal to x plus I by I over h cross p dot dx dash, commutator of p dot dx dash x. Okay, that is equal to x plus dx dash, and I'll show you how the steps which led to this equations. That is it's a lengthy steps, and I'll explain briefly. I'll explain rapidly. Just listen it. 1 plus ip dot dx dash over h cross x 1 into 1 minus ip dot dx dash over h cross, that is equal to we have to multiply 1 into x into 1, we'll get x, and then we have to multiply 1 into x into this term, so that we will get x dot ip dot dx dash over h cross plus then we need to write 1 into x into this term, so we'll get this one, and then finally this one into x into this last term. Usually we used to multiply like this, and we'll get this term. Listen, look at this term here. Dx dash, operator dx dash comes twice, or dx dash is multiplying. That means dx dash is a number, dx dash is infinitesimal translation. This is a small distance that is equal to a number into an identity operator into some particular direction. Okay, so it doesn't matter where we are using this operator. Okay, that means if you are multiplying dx with the dx, then we will get dx dash square. this is very small term, so we can second order term of this small distance dx dash is too small, and so it is negligible. Okay, so this term, this is approximately equal to x plus, we used to ignore this term. So that is equal to x plus ip dot dx dash over h cross x minus x ip dot dx dash over h cross. We can take this I by I over h cross outside, and then we will get p dot dx dash x minus x p dot dx dash. That means in the form of ab minus ba. That is equal to commutator of ab. That here I can show. That steps which I told, that is equal to x plus I over h cross p dot dx dash, commutator of p dot dx dash x. Okay, and then that I got here, that step I have written here, and then we will come to the steps. Okay, this will take two lengthy steps to reach at that point, and I'll explain rapidly. That is equal to x plus I over h cross. We can expand this. This is actually vector p. So px dx dash plus py dy dash plus pz dz dash, that is p dot dx dash, and xi plus yj plus zk minus, then we will expand this next term like this. Okay, and then we need to multiply this with each term x, y, z. Okay, that is happening in this steps, and we have done it. And after that is equal to x plus I over h cross. I over h cross, we are taking the I term, x component, that is here one x component is there, here also x component is there, so we are taking px dx x minus x px dx dash. Okay, px dx dash x minus x px dx dash into I cap. Okay, then plus another second term py dy dash x I minus next term with the x component is x py dy dash, like that we are taking. Okay, I am not writing the whole steps because it's too lengthy, so you have to assume, or you have to derive the steps by yourself. That is equal to x plus I over h cross dx dash. Here I can take this dx dash outside because dx dash is a number into an identity operator in some particular direction. So it doesn't matter where this operator is using. We cannot write px x equal to xpx, but we can write px dx dash equal to dx dash px. Okay, because this is a number into an identity operator into some particular direction. Okay, so dx dash I have taken outside of this bracket pxx minus xpx plus dy dash pyx minus xpy. Okay, and that is equal to x plus I over h cross dx dash pxx. Okay, this I can write, this is ab minus ba, so I can write pxx plus this is this I can write dy dash pyx pyx plus etc plus etc plus dy pyy plus etc plus dz dash pz z plus etc. Okay, you have to fill the blanks, and I just selected some specific terms only because only this terms will be useful. Rest of the terms will be equal to 0 because this is pyx and this will be equal to 0. We have learned commutator brackets, and this is y component of momentum, and this is x component of position, and this will be equal to 0 when it commutes. Okay, so the remaining three terms are there. That is equal to x dash x plus I over h cross dx dash pxx plus I cap pxx I cap this Here there are I caps are there. I just forgot to write it. Okay, here I caps are there, I cap, j cap, k cap, and this whole components and the component terms are there. So I just forgot to put that one. Now I am putting this I cap, and here also I cap. So this is I cap, here it's j cap, here it's k cap. Okay, so that is equal to x plus I over h cross dx dash pxx I cap plus dy pyy j cap plus dz pz z k cap. Okay, that is equal to x pxx commutator of pxx equal to minus I h cross we have learned earlier, that is and pyy also minus I h cross, pz also we will get I h cross. Okay, so the next step is that is equal to x plus I over h cross dx dash minus I h cross I cap plus dy dash into minus I h cross j cap plus etc. That is equal to I over h cross into minus I h cross dx dash I cap plus dy dash j cap plus dz dash k cap equal to x plus this h cross will get cancelled, and this minus sign also will be plus, and that is equal to x plus dx dash. Okay, so we got the transformation of operator x into x plus dx dash. Okay, here the operator is changing by approach 2 that I have derived here. The operator is changing, x is changing into operator is changing into x plus dx dash by approach 2, and the expectation value of this operator x will change into x plus expectation value of x plus dx dash. That is if you are taking the expectation value of x plus dx dash, that is alpha with respect to alpha x plus dx dash, alpha x alpha plus alpha dx dash alpha into x plus dx dash. Okay, now let's discuss state kits and observables in Schrodinger and Heisenberg's picture. Here we are taking a time evolution operator, and that's a unitary operator. U of t not equal to 0. We are taking initial time equal to 0, that is equal to u of t equal to e raised to minus iht over h cross. This is the form of time evolution operator which we know. By approach 2 we define. By approach 2 means the operator is changing with respect to time. Okay, that is Heisenberg's picture. Let me take an operator A, and considering that operator in two perspectives. One is Heisenberg's picture and another is Schrodinger's picture. In Schrodinger's picture, or in Schrodinger's perspective, the operator is not changing, but in Heisenberg's picture the operator is changing as u dagger t a u of t. Okay, this operator is changing as u a u of t. Okay, at time t equal to 0, a in Heisenberg's picture of 0 equal to a in Schrodinger's picture. Okay, at time t equal to 0, this operator is changing with respect to time. Operator is changing with respect to time, and when time t equal to 0, this both pictures coincide. That means the operator in Heisenberg's picture coincide. That's equal to operator in Schrodinger's picture. Okay. And the state ket, when we are considering the state ket, in Heisenberg's picture, alpha t not equal to 0 t in Heisenberg's picture equal to alpha t not equal to 0. because in Heisenberg's picture we know only the operator is changing with respect to time, not the state ket. So this both will be equal. Okay, here the state ket is not changing with respect to time. After a time t equal, after a time t also this is alpha t not equal to 0. In Schrodinger's picture, the state ket is changing. Okay, alpha t not equal to 0 t. That means when we are operating with the time evolution operator on alpha t not equal to 0, we will get the Schrodinger's picture. That means the state ket is changing here, not the operator is changing. And earlier we discussed the expectation value of an operator is obviously same for both pictures. Okay, the expectation value is not changing with respect to time. With respect to time when we are considering the approach 1, that is Schrodinger's picture, or when we are considering approach 2, that is Heisenberg's picture, our expectation value should be same. This mathematically we can represent as Schrodinger's alpha t not equal to 0 t. A in Schrodinger's picture, alpha t not equal to 0 t, that is equal to alpha t not equal to 0 u dagger A in Schrodinger's picture u alpha t not equal to 0, because when we are operating this u dagger with this one, we will get Schrodinger's picture. Okay, because in Schrodinger's picture the state ket is changing, not the operator, and that is equal to we can represent like this, and that is equal to we know u dagger A in Schrodinger's picture, u equal to operator A in Heisenberg's picture is this one. Okay, the expectation value in Schrodinger's picture and the Heisenberg's picture will not change with respect to time. And let us discuss an important topic, that is the Heisenberg's equation of motion. Assuming A in Schrodinger's picture, operator in Schrodinger's picture does not depend explicitly on time. Okay, this operator is not explicitly depend on time. That means when we are taking a partial derivative, we can take the operator A as constant. That is we used to express in this way. That means explicitly, does not depend explicitly on time. That means when you are taking a partial derivative of operator A in Schrodinger's picture, that will not change. Okay, in the outset we defined our operator x is changing as u dagger x u. Okay, with state kets unchanged. So if we are considering an operator A in our Heisenberg's picture that changes, as u dagger A u. Okay, A, yes, this is in Schrodinger's picture. This changes like this in Heisenberg's picture. Okay, so if you are taking the differential of Heisenberg's differential of operator A in Heisenberg's picture, that is dAh divided by dt equal to we can differentiate it dou by dou t of u dagger A in Schrodinger's picture into u plus, okay, u plus A of s into dou u divided by dou t. We can differentiate A of h in this way. That is equal to dou by dou t of u dagger equal to e raised to I h t over h cross, and u equal to e raised to minus I h t over h cross. So dou u dagger by dou t means dou by dou t of e raised to I h t over h cross A in Schrodinger's picture u plus u dagger as in dou by dou t of e raised to, that is this one is u dou u divided by dou t, that is equal to when we are differentiating with respect to t, we will get e raised to I h t over h cross I h cross I h over h cross a in Schrodinger's picture u plus u dagger as e raised to minus I h t over h cross into minus I h over h cross. Okay, this I can write, that is equal to I over h cross u dagger h a in Schrodinger's picture u u minus I over h cross u dagger as this is actually u. I put it with this h cross, so that's why this minus sign came. So that is minus the I came into denominator, that's why this minus sign came. That is minus 1 by h cross u dagger h. I just put a u dagger. This is equal to actually 1. This identity operator, like multiplying with 1, that's a as u, and plus. Okay, this I brought into denominator, so this minus sign became the plus sign. So 1 by I h cross u dagger as u h. I have written h u because actually u equal to e raised to minus I h t over h cross, and this is another operator h. Actually this u and h commutes, because of that I can write u h into u. Commute means when we are operating with this one first and then this one equal to we are operating this first and this one. Okay, that's the meaning of commutator of uh equal to 0 or h equal to 0. So I can write in this way, that is equal to minus 1 by I h cross u dagger h u dagger as u plus 1 by I h cross u dagger as u dagger. I just put 1 u dagger because this is equal to 1, will not make any difference in this equation. H u, that is equal to minus 1 by I h cross u dagger h u. Actually this term is u dagger as u, we know that is a in Heisenberg's picture that I have written here, plus 1 by 1 over I h cross a here. This is also in Heisenberg's picture, u dagger a Schrodinger's picture, u equal to a in Heisenberg's picture, u dagger h u. Okay, this is, I can take this 1 over I h cross outside, and I can write this in the form of if you are taking a, this is b, this is b, this is a. That means ab minus ba, commutator of ab. Instead of b, here it's u dagger h u. Here I can write u dagger h u equal to h, because u dagger is e raised to I h t over h cross, and this is h, and u is e raised to minus I h t over h cross. Okay, so this u and h commutes, because of that I can write e raised to I h t over h cross into e raised to minus I h t over h cross into h, and this will get, we will get as 1, and we will get that is equal to h. So I can write this equation dA in Heisenberg's picture over dt equal to 1 over I h cross commutator of a h in Heisenberg's picture, comma h, commutator of a and h. This is known as Heisenberg's equation of motion. Okay, this equation we have derived using time evolution operator. Alright.